Well, good evening and welcome to Thursday Night Pre-Calculus. My name is Curtis Brown and I have with me Vicky Carter and Steve Kokoska. I've got Tom Dick here to do a little bit of calculator stuff. Just in case you were wondering, I have not done my homework. And so I will not be answering a whole lot of Steve's questions, but I would love it if the students out there would be ready and willing to join in answering questions. Of course, teachers, we have the content down in the description. As always, I'll make sure and get uh, that link out there to you guys here in just a second in the chat. But go ahead and put where you're from, where you're watching from in the chat, just so we know who's out there watching. Students, I know that there's several teachers that ask for your notification in the chat as well. So make sure that you identify yourselves and say hello. Anyway, with that, I will let Steve take it away.
Thank you very much, Curtis. All right, I think I've got my screen shared. It's great to be with all of you tonight, Vicky, Tom, Curtis, and we have another person. We have a guest tonight from TI, Michelle. So I think it would be fair that we ask her a couple of questions too. So Michelle, maybe you had the chance to do some of your homework too.
Better watch out.
As we begin to look at some of this, we'll be graphing some polar equations tonight. And of course, technology is a great help in doing this. And Tom and Vicky and I were probably ashamed to admit, but we probably remember graphing these without technology and how painful that was, and how nice it is now to have a TI-84 or even a TI-Nspire to help. This is really cool. So the first one here has a polar function, r of theta, given by -2 sine theta for 0, less than or equal to theta, less than or equal to pi. And I asked you to complete a table of values here and use that to help sketch the curve. And I'm going to go back and forth between the table, a little bit on the side here, and this graph. I've actually got some points marked on this curve. So the first quick one I'm going to take a look at, and I'm going to do a little bit of this by hand if I can off to the side here. If we let theta be equal to 0, the sine of 0 is 0. So the first point is at the origin, and I think I've got that marked in there. Curtis, Michelle, I don't know if you can see this, but there is a little bit of color in there. The actual polar curve is in blue. I do have a polar grid sort of superimposed on an XY grid, which helps me a little bit. I don't know if you can see all of those grid lines, but I think that's kind of a neat graph. I don't see that too often, but it helps me a little bit graph some of these. So, all right, I'm going to try theta equal to pi over 6, and I'm over here on the right-hand side. So I'm looking at r of pi over 6. That's -2 times the sine of pi over 6. So let's see if I've got this right. That's -2 times 1/2, I believe. So that's going to give me a -1. And let's see if I can graph that. So I really have to graph this pair of theta r or r theta -1 pi over 6. Well, let's see, it's kind of hard to see my grid lines where I am, but I'm at a pi over 6 out here and 1 unit along that ray. But wait a minute, r is negative, so it's through the origin, it's on the other side of the origin. So that means it's this point right there that corresponds to pi over 6 -1. Remember, we draw that line through the origin with reference angle pi over 6. Since r is negative, it's down there in the third quadrant. Let's try another one.
Steve, hang on just a second.
Shoot, go
I
ahead.
think you hit pi over 4
Oh, I
rather
think I
than
did
pi over
too.
6, but
Yeah,
just
it's
to make
hard
sure
to
we
see.
don't confuse anybody.
I'm sorry, it's hard to see my grid lines here.
There you go. That's the right one.
The one, yeah, there we go.
Yeah,
Thank
there we go.
you. Thank you. Okay, so -2 times the sine of pi over 4. There we go. -2 times the square root of 2 over 2, I think. And I know a lot of people like to write that as 1 over the square root of 2. I guess I always learned it this way, sort of rationalized. So that's a minus square root of 2. And let's see, can I get this one right here, Vicky? Let's see, there's a minus pi over, pardon me, pi over 4. Let's
Yep,
see.
that's it.
That's it. Okay, there we go. And we got to go in the opposite direction again because, let's see, r is negative. So I think it corresponds to that point. And I'll just make an observation because I know what's coming here. I know that that the square root of 2 is bigger in magnitude than 1. So it seems like r is getting bigger negative, if I can say it that way. It is decreasing. What happens when theta is equal to pi over 3? Well, let's see. Now I've got a -2. Let's see, times the sine of pi over 3. That's the square root of 3 over 2. A little bit of canceling. That's a minus square root of 3. That's a 3 right there. So let's see if I can get this one now. Let's see. That's a pi over 3. So I think let's see. Have I got it right there, Vicky?
Yeah, you've got it.
Okay, kind of hard to see. Going through the origin again because r is negative, so that's that point. So, all right, I found some more of these points. I plotted them on my polar grid, and I realized, you know what, this sure looks like a circle. I connected all the dots. Indeed, this is the graph of a circle. It's centered at at 0, -1. And I think that Tom, in a minute or two, will show us some neat ways to graph this using technology. We'll get there in a minute or two. Got a couple quick questions about this graph and about r. It says first, on the interval 0 to pi over 2, how's the distance between the point r theta and the origin changing? Well, let's see. We just kind of worked through all of that. And we saw that as theta was increasing between 0 and pi over 2, we can kind of see we're moving along this circle in this direction. And we can see by looking at these values of r that in fact r is negative and decreasing, getting bigger negative. And that tells us that the distance between that point and the origin is increasing. And we can visually see that. The point on the curve is getting farther away from the origin. That's kind of cool. I'm going to just arrow up a little bit more if I can. Hey, how about that? And now between pi over 2 and pi, well, okay. I completed my table, and I found that as theta varied between pi over 2 and pi, I'm moving along the circle in this direction. I plotted a few more points. I looked at the value of r, and I recognized that r is negative, but it's increasing. So it's negative, but it's increasing. And that tells me that r of theta is getting the distance between r theta and the origin is decreasing. I should probably change this, I think, here. It should probably be consistent and make that an r comma theta. The distance between that point and the origin is decreasing. So that's kind of a neat short example to start with, plotting that by hand, thinking about how we're moving around that circle and how the distance between the point and the origin is changing. I apologize. Did I have a part D here? I think I had a very short one. It says for theta in that interval 0 to pi, what point on the polar curve is farthest from the origin? Well, I'm going to sneak back here and look at that polar curve for a second. And looking at my grid up above, looking at my table up above, looking at my graph, the point that is farthest away from the origin is right down there. And let's see, that's the point -2 pi over 2. Pretty good.
So Steve, just to
Yes,
mention to students that are participating tonight,
yes,
that
please.
connection of r being negative and decreasing on that interval from 0 to pi over 2
Yes.
with the fact that the distance between the point r theta and the pole is increasing is a very important connection that they need to make. I also do want to mention that all of the questions on the AP exam on any of the polar work will be multiple choice questions. There's nothing in the free response questions on the three topics that are on the polar coordinates and polar graphs and rates of change.
So Vicky, let me ask you, on this particular question, I think I could answer B and C by hand if I had to, by completing a table of values. But would there be a question like this, do you think, that would be calculator active? Where a
It
student had?
possibly could be, especially if the graph were something that um, not one of the fairly familiar functions that we may know.
Yes.
Um, I mean, that's always a possibility. A good many of the questions, though, are in the no calculator part where they actually, in many cases, they have the graph to kind of look at. And I
Yes.
think a lot of the teachers are also helping students understand that connection that we talked about in a previous one of these sessions,
Yes.
the connection of the rectangular graph with the polar graph and how they
Yes.
kind of both help you understand what's going on.
So if it were on a calculator active portion of the
Hmm.
exam, I assume that students who have the graphing calculator in front of them can graph a polar curve, could actually use trace mode to kind of see,
Yeah.
right, if the
I
distance.
would I would definitely recommend that because the trace mode is pretty much as you trace, you're going through those increasing theta values, and so it should be somewhat obvious what's happening with that distance between the pole and the point on the polar curve.
Absolutely. Okay. Excellent. Thanks, Vicky.
You're
Tom, can
welcome.
we try a little technology?
Sure, Steve. Be glad to.
Okay.
All right.
Coming at you. There you go.
Okay, I'm going to share my TI-84 screen. I hope that's coming up okay for y'all. And with polar, I'm just going to kind of take it from square one here. Maybe I should say circle one to look at, you know, using the graphing calculator to work with polar equations. As Steve said, it can be, especially for a complicated expression, it can be somewhat tedious and time consuming to make a graph by hand. That said, I'm hoping everyone does provide that experience for their students. I think, in polar graph paper or grid paper is really helpful to get the experience of how that polar graph is generated. But when one wants to do some explorations with a variety of graphs in polar mode, the graphing calculator is a really invaluable tool. So let's get started. Let's actually use Steve's example here. Very first thing I'm going to do is go to the mode menu and arrow down to that line that has function, parametric, polar. These are different graph types. Probably 90% of the time, at least, you're in pre-calculus, you will be in the function mode. But for this, we're going to want to go to polar mode. So I arrow over to polar, enter that.
And Tom, while you're on that screen,
Sure.
everybody needs to make sure that they're in radian mode because that's the only mode that we deal with in AP pre-calculus.
Absolutely. Yes. Then radian mode, we can see there up at the top that we're in the right mode there. Okay. Now I'm going to go ahead and go to my y equals menu. And wow, it looks different. Okay. Instead of y1, y2, and so on, we now have r1, r2 up through r6. And so this is set up for polar equations. Let's go ahead and put in the one that Steve was working in with. I think it was -2 times the sine. Oh, theta. Where do I get a theta? Well, when you're in polar mode, that x comma t theta n key is now a theta key. So it's sensitive to which mode you're in. So I'm just going to hit my xt theta n key. There's a nice theta there. Okay, great. All right, looks good. And let's go ahead and graph. I'll just go ahead and do a zoom decimal. That's kind of my favorite window, kind of by default. Boom, there's that circle that Steve got. And now I'm going to try a trace and see what happens there. All right. Now this is, okay, this is interesting. I should relate something that happened to me a little while earlier today when I was playing around with this. Notice that my trace coordinates are in polar coordinates.
Yeah.
That might not happen the first time out. In fact, if we go to format, you'll notice at the very top there, there's rectangular GC, that'd be graphing coordinates, or polar GC. And I had mine changed over to polar. What would happen if we changed it to rectangular graphing coordinates? Let's go back to the graph, hit trace again. And notice now we still have that theta value, but now the coordinates are being reported and rectangular form. And you may actually be doing some work where you're dealing with both because you're wanting to know what those coordinates look like in rectangular form or polar form.
Yeah.
I think for a lot of our basic graphing, if we're graphing in polar, we're going to want to be in polar graphing coordinates. So let me quickly change that back. Oops, let's try that again. There we go. Polar graphing coordinates. And I'll turn the trace on again. And as I do a right arrow, the right arrow is actually incrementing theta. So theta values are going up, but notice my crosshair went to the left. And that's because it's traveling around that circle in that direction. Now those theta values, it looks like they're incrementing by kind of a weird amount. Let's see, what was the very first one we hit? Looks like 0.130 something. I'll just go ahead and let the cat out of the bag. You can do a little calculation to figure out what this is, but it's actually pi divided by 24. And so that's a kind of a reasonably small increment, but if you think about it, that's going to naturally hit all your common multiples, rational multiples of pi. So pi over 6 is 4 pi over 24. Pi over 4 will be 6 pi over 24, so you're going to hit each of those values. So we can trace around, and we see we're getting negative R values. And boy, you know what I'm really wishing I had as I'm doing this would be some kind of background polar grid that we can look at here. And that's not something that's built in to the 84. I'm going to show you, though, a little program, and I think Curtis can correct me, but when he makes the problems and solutions available, I think he could make these programs available. I'm sure they're on the TI website, but for ready access.
Yeah, we'll put them in the description. We'll link that there too. Not a problem.
Tom,
Yes.
before you do that grid, just one quick question. I've forgotten, is it possible when you're tracing to actually type in a value for theta?
Oh, absolutely. So, for example, if you've got a favorite one, Steve.
Yeah, just for the heck of it, can you type in a pi over 4? I know it won't display that way, but if you type in a pi over 4.
All right, let's try it. So I'll find the pi divided by 20, or 4, excuse me.
Yeah, 4.
Yeah. 24 is the increment. Okay. Let's see if it'll jump to that. Boom.
Great.
There we go. Great.
So that number, that value of R looks familiar and would support some of the stuff that I did by hand. Yeah.
Yes.
Okay,
and
good.
the location looks good. If I imagine
Yes.
a ray emanating from the origin to that point,
Yeah.
well, it actually looks like we're at 5 pi over 4, doesn't it? Pi over 4 would be up here in the first quadrant.
Yeah.
What's going on there? Well, it's that negative radius. So
Yeah.
it's gotten reflected through. Also, a reality check looking down here at theta. I mean, pi is a little bit more than 3. So pi over 4 should be just a tad over 3/4.
Yeah.
Looks good. Point. So
And Tom, you know, you're the most incredibly lucky person because that circle actually looks like a circle.
Well, that's one advantage of the zoom decimal window. One of the reasons I like that particular window is things are squared up. And so the distances are not going to be distorted by having unequal scalings on.
Yep. Cool.
Otherwise, it's going to look kind of elliptical.
Yes. Yeah.
All right. Well, let me quit from there and show you this little program. So I'm going to go to programs. It's a TI basic program. And you can see I've got a couple of them here. One says polar GRD, that's for polar grid. And the other one's even more simple, polar off. It turns off that grid. Okay. And what this polar grid does is it actually makes use of some lists of values in the stat plotter to plot a bunch of lines and circles to create a kind of a background grid. And this grid is done in gray, so it doesn't, distract. It gives you some background but you can still tell where your function graph is.
Mm-hmm.
So let me go ahead and enter that, and I'll hit enter one more time to run it. And now let me go back to the graph and see what we've got here. Oh, there it goes. It went
Oh,
back.
that's
It
cool.
took a while to plot those things, but now we have this polar grid, and I think it's actually pretty close to identical to yours, Steve.
Yeah.
I was looking at yours, and these rays here are spaced at pi over 12.
Right. That's what I did. Yeah.
Because
Right.
there's 6 of them between 0 and pi over 2. So I did a little arithmetic there. That looks good. Okay. So pi over 3 is this one, and pi over 4 is on that diagonal line, pi over 3. This one here's 5 pi over 12, which we don't use that often, but occasionally. And then there's pi over 2. But now we have that superimposed. I could trace again. Oh, notice what came up here.
Oh, yeah.
You can barely see it since it's in gray. It's showing me the stat plot. So let me arrow up and get on the actual graphing the polar plot. And now we can again, trace, but we have the advantage of being on that grid. And I think that to me, I really like having these kinds of background grids available when I'm doing polar, because for a reference system, helps me visualize exactly what's going on.
Very cool.
Yeah,
Now-
I think that would be very helpful to the students that are using the TI-84.
Yeah.
Now, just a little warning about this grid is it's there now for good. Well, really, it's there until you actually turn it off. So if you were to go into doing some just regular y equals f of x type of function plotting, that grid is still going to be there in the background. And so if we quit here and we want to remove the grid, we'll just go back to program, to TI basic, that second program's polar off. And it just basically clears out all those lists, and as well as clear the screen. And so after we run that, if we go back to our graph, it's cleared out again without a grid. So those two programs, I think you want to pair them up. And to be honest, I'm not a huge fan of having just tons and tons and tons of programs, but there's a few utility programs I like to have on my 84. And these are a couple of them for polar for sure, is that grid. So, and you actually saw one of the others that we'll do at some point. That's a slope field program, but that's a topic for calculus topic for some other day. All right. I think I'll turn it back over to you, Steve, unless you or Vicki have something you want me to take a look at while we're here.
I'm good. Vicki?
I'm good.
All right.
Curtis?
I'll pop the share and
Okay.
there we
go. Okay, there we go. So problem 2 that I've got set up here is similar, produces a different graph, but similar in nature. Let's take a look at r of theta equal to 3 cosine of 3 theta between 0 and pi. And once again, let's complete a grid, use some of those values to try to sketch this curve and try to figure out sort of in which direction we're moving here as theta increases. So, okay, for theta equal to 0, let's see. If I plug in a 0 there, cosine of 0 would be 1. So, okay, I can see the 0, 3. So this is interesting. Sometimes when we when we sketch the graph of a polar curve, we sort of instinctively believe that, well, we always start at the origin and we always start at the pole. And that's not true. This one actually starts at the point, well, in x and y coordinates at 3, 0. In r theta, it's 3, 0. Okay? Also 3, 0. How about that? So let's see. Pi over 6. What happens when theta is equal to pi over 6? I plugged that in over here on the right-hand side. Again, bear with me. Allow me a little literary license here, doing some of this by hand. So 3 times the cosine of 3 times pi over 6. So that's really a pi over 2 in there. So that means this expression is just going to be 0. So the whole thing is 0. So here's the second point that I've got. I'm really at the pole. I'm really at pi over 6 is the value of theta, but r is 0. So I'm back at the pole. So given this first point, I'm going to conclude here that I'm moving along this curve in this direction here as theta increases between 0 and pi over 6. Now you can kind of see and you can kind of feel this curve and suspect where it's going after that, but let's see if we can confirm some of this. If I let
So
theta,
Steve, I'm
oh,
going to
go ahead,
interrupt you a second before when
please.
you say see and feel the curve,
Yeah,
it instantly comes to mind. And I have recommended this to a lot of AP pre-calculus teachers to find an old spire graph, and you can still buy them. And it
yeah,
gives the students the sense of how this, like those discs roll around inside
yeah,
that
yeah,
circle. That's what's actually happening here, and I think it gives them a better sense for how these graphs evolve.
yeah,
And we've experienced this a lot. We've looked at lots of these, so we have that thought in our minds as we roll around this graph. But for pre-calculus students, this is going to be very new to them.
yeah. And you know, one might expect that there could be some sort of sharp edge or sharp corner in this kind, right? But there isn't. This is nice and smooth, as you say, tracing around with a spirograph. It is nice and smooth with no jagged edges, sharp turns, or anything like that. Yeah,
Right.
true. Very true. Well, let me see if I can justify the next point on my curve. Let me see if I can get this. When theta is equal to pi over 4, I'm going to plug in a pi over 4 over here. So I've got a 3 pi over 4. The cosine of 3 pi over 4, well, let's see, I got to think about that a little bit. It's going to be over here in the second quadrant. So that's a minus square root of 2 over 2. There's no cancellation there. So I guess this is equal to a minus 3 square roots of 2 over 2. And I wrote it like this without that rationalization. I'm not sure exactly why, but perhaps to help me in questions to follow. So let's see if I can see the gray grid lines. And again, I apologize, Vicky, kind of hard for me to see on my graph, but let's see. Is that pi over 4 right there? I think it is.
Looks good.
Yeah, I think it's right there.
Yes.
Okay. So there's pi over 4, but wait a minute. Let's see. R is negative, so it's got to be on the curve opposite, pardon me, the line opposite that to the origin. That's a perfectly straight line. So it's down there. It's down there actually in the third quadrant, isn't it?
Yes.
Let me try one more, okay? So when theta is equal to pi over 3, I'm going to plug that in. The 3's will cancel, so I've got the cosine of pi, which is just a minus 1, multiplying by 3, that's a minus 3. So, okay, let's see. When I'm at pi over 3, let's see if I can get this one. That is up here along
Yes.
that grid line. But again, R is negative. So we're on the opposite side of the pole, and that's going to be through this line right down there. There's that point. So I'm sorry, my graph is a little messy, but I'm going to try one more time here. Here we are tracing out this curve, and it's going like that. And then I think it's going to come up here. And like that, and back over where we started. Do we call this a 3-leaf rose? How
Or
about
three
that?
petal rose,
Or a
whichever.
2-petal rose. How about that? That's kind of cool. All right, let's see if we can answer some of these questions below. See if I can get this. On the interval between 0 and pi or 6, how is the distance between that point on the graph and the origin changing? Well, okay, this is what we discussed early on in graphing this. I think we start over here at this point, and we're moving in here. We can see visually that the point on the curve is getting closer to the origin. In AP pre-calculus lingo, R is positive and decreasing, and therefore the distance between the point on the curve and the origin of the pole is decreasing. Good, I got that one. I can see that one. And let's see if I can arrow up just a little bit. Any chance of that? There we go. On the interval between pi over 2 and 2 pi over 3, how is the distance between the point on the curve and the origin of the pole changing? Well, let's see here, between pi over 2 and 3, 2 pi over 3, where is that, I wonder? Well, I'm going to have to sneak back up here and take a peek. Pi over 2, oh, wait a minute, let's see. When theta is pi over 2, take a look here, r is 0, so where am I on this curve? I'm at the pole. So I've actually come all the way around here, And now I'm at the pole, and as theta increases, let's see, it's actually going to be moving up along here to this point. Notice when theta is 2 pi over 3, there's a lot of symmetry here. I'm a distance of 3 units from the pole, from the origin. So between pi over 2 and 2 pi over 3, I believe we're looking at this part of the curve right there. I can see from looking at the curve that the distance between the point on the curve and the origin is increasing. How do we justify that in AP pre-calculus lingo down at the bottom? Well, R is positive and increasing, and therefore the distance between the point on the curve and the pole is increasing. That's pretty cool. And now I need to think a little bit more about this one in order to answer part D. For what values of theta is the point on the curve farthest from the origin? Well, we've actually seen a couple of these already, didn't we? We saw one here where it was 3 units away from the origin. We saw another one here, and with a little bit of symmetry, there's one there. What's this point correspond to? Well, actually, 0 and pi. We know we've got a complete graph from 0 to pi, and we know we started out over there at that point, 3, 0. We know this point down here, I think we talked about that one already, didn't we? That's pi over 3 minus 3. And we've actually got this one too. I actually computed this one by hand. That's a 2 pi over 3 for theta, and r equal to 3. So there are some, those are the farthest points from the origin or from the pole. So I think I've got them listed down there: 0, pi over 3, 2 pi over 3, and okay, pi, we're back where we started. That's pretty cool. Pretty good. Tom, before I get to 3, do you have a little bit of technology that you can show on this one?
Sure do, Steve. Yeah.
Okay, good. Very good. There you are, sir.
Okay. All right. I'll go back to my TI-84 screen here. I hope that's coming up. Let's see.
Yep, got it.
And, let me go ahead and do a couple of things here. First of all, I'm going to go ahead and get that grid up again.
Okay.
And so I'll go to my programs, polar grid, execute that. And it takes a while because it's actually doing several scatter plots. There we go. Very nice.
Got it.
Let me go to my y equals menu, which is really an r equals menu in this case. And let me change my function here to the one you were looking at, which was 3 times the cosine of 3 theta. Oh, it looks like I think I got it.
Hey, how about that? That was pretty good, Tom.
Very good. Very good. All right. So let's go ahead and graph this. Yep, there we go. It looks very nice. Okay. And again, we could trace and
whoops, did we lose Tom?
for my theta. Way out there. Will it work? Let's see. Oh, let's see. Now, it says it's, what is it saying here? It's not valid. Let's see. Okay. This is bringing up something I want to point out. If we go to the window, and that's something we didn't look at, we hit quit first and go to the window.
Yes.
You'll see that the window settings are also different for polar than they are for function plotting. So we have a theta min and a theta max. Besides, we still have our regular x min and x max to define the boundaries of the window itself, but we also have a theta range for our independent variable theta. Okay, so I could set that. You can probably recognize this. It's the default here was 0 to 2 pi. And I said that theta step was basically pi over 24. I wonder if I went down here and made theta max, say 30 pi. Okay,
Holy Toledo.
there. And if I graph that, I wonder what that'll look like. Oh, it looks identical to what it was before. We had a much larger theta range. And if we think about that, well, it is a cosine is a periodic function. So it's just kind of retracing that three-leaf clover or whatever you want to call this over and over and over again. Now, I wonder if I did a trace now, get to the polar curve, I wonder what would happen now if I tried something like 25 pi for uh, the value of theta. Ooh, goes right to it. So we can see what the problem was. It was paying attention to the range for theta that we had set up. I really should say domain for theta because it is the independent variable here. So we can jump out to there, okay? Now here's what I think is so beautiful about doing these things with graphing calculators is it said this is not one that's bad for plotting by hand. But if you want to start playing around with ideas like the following, let me go to my y equals menu. I'm going to make a couple of edits to this. You have 2 3s showing up here.
Yeah, sorry about that, Tom. That was my fault.
No problem. Okay. Yep. Oh, no, that's not bad. Sorry, my phone was going off. I hope I just had to turn it off. Okay. I'm going to change one of those 3s to a 4.
Okay.
And the other 3, I'm going to change to a 5. Okay. Now we can just jump in and plot, but we might want to take a pause and think about, well, what kinds of changes could this make to the graph? Okay.
Mm-hmm.
I noticed that the links, the radius of your leaves, the outermost tips of them were 3 units out from the origin,
Right.
and there were 3 leaves. Well, which one of those numbers is controlling what? Okay, so is this going to be a 4-leaf clover or 5-leaf clover? Neither. How big are the leaves going to be? And after we think about that, we can, try to verify by looking at a graph. And looks like there's 5 leaves to this. Folks may be a little bit concerned about how choppy this looks.
Yeah, how can we fix that, Tom?
I'm glad you asked, Steve. So I'm going to go back to my Windows settings. And if we want it to be a bit smoother, we can just go down to the theta. Well, one thing I will do, I'll change my theta max down to 2 pi again.
Okay.
Though that's not the fix.
Okay.
The fix would be to use a smaller theta step.
Okay.
Okay. Now I could just put in a small decimal number, which would be fine.
Mm-hmm.
Or if you're really still wanting to hit those really nice values of pi, we could do something like do a pi divided by something that has common factors of, it should be a multiple of 24 if we want both kind of 4 and 6 in there. Okay.
Gotcha.
I'll tell you what, I'm going to put 96 there.
Okay.
And now we'll enter that graph again. You can see how much smoother it is. Okay, now we have a much smaller increment for our theta. So if we do the trace, we get on the polar graph, as I increment theta, you can see now it's incrementing only by about 0.03 each time. Notice that it took me 4 of those to get to what was pi over 24 before.
Yeah.
But we can jump to, if I want to jump to pi over 3, do that. And we see the radius is exactly 2 there.
Wow.
Oh, I'm also seeing that my radius, I can count these concentric circles. They're 1 unit apart in radius. Mm-hmm. 1, 2, 3, 4. Okay. So that leading coefficient is controlling the radius of our leaves. And the coefficient of theta is controlling the number of leaves that we get, which is kind of cool. So we've got a whole family of these flowers, if you will. Yeah.
So Tom, you may be about to go here, but what if we reverse the 4 and the 5?
Great. That's right. So went back to the R equals menu. I'll change that to a 5. Let's change the 5 to a 4. And graph.
Holy Toledo.
Ooh. So that 4, it changes, it definitely affects the number of leaves, but maybe in a way that we didn't expect.
Yeah.
So teachers that are listening, I think it's very important for you to have your students using technology to do some explorations and see if they can deduce what's happening when that n times theta or whatever variable, whatever number that you're multiplying theta by is even or odd, and see if they can come up with it.
Tom, I have 2 questions for you. One, I don't want you to do this. Just give me a yes or a no. Does this work? Does polar graphing work with the Transform app?
I do not know. I'm
Okay.
pretty sure it
Maybe
doesn't.
Curtis can chime in.
No,
Okay.
no, it does
It
not
does
work with
not?
the trans.
Okay. Could you go back to y equal for a second?
Sure. Yeah. In fact, Steve, I was able to answer it fairly quickly because I'd been thinking about that with this problem just earlier. It'd be kind of neat if we could.
Yeah.
What we
However,
could do is we could replace this with an A and a B,
Yes. Yeah.
and then on the home screen you could change the value of A and B. But you would
Yeah.
be doing it wouldn't be quite as slick as that transfer.
I'll do you one more, one in between even yet.
Okay.
You could replace that 5 with a list.
But
And
that will plot all of those.
That would plot them subsequent. That would plot them, one at a time. But you've got a family of functions then that you could skip between, and look at, tracing them. So if you made that, if you said, say, make that list 1 or something, or you could put your own little list there. That's fine. 1, 2, 3 or something. And insert a list that way. Now you could, if you draw that graph, you got 1, 2, 3. Now they're all the same color, so it doesn't change the color.
Right.
But when you hit the trace key now, you can go around the 1. And so you'll hit the up arrow.
Okay.
And you'll be able to see, if you hit the up arrow again, now you could trace around the 1, and then you could trace around the 2.
I want to go that now. Notice I've got those stat plots that are
there you go.
those things.
Yeah, sorry.
So
So there you go.
That's one price I'm paying for these programs. Yeah.
Right. So now you've got those, and now you can trace right and left. If you use the right and left arrows, you can trace around each one of those individually.
Yep. So here we're on the middle curve in a sense. Middle in the sense has the middle radius, if you will.
Right.
Lengths.
So that's at least a step where you can kind of see the differences between those in the list. As you generated those values. So.
And I know folks that their students have just gone to town with polar plotting, in just in terms of generating cool pictures.
Yeah.
It gives you a flexibility. Like this is really lots of symmetry going on with this picture, and very neat.
Tom, would you try one more thing for me? If you go back to y.
Oh, if I have to, Steve, I will.
I'm sorry. Would you delete that list and just put a 3 in there? Just make that 3 times cosine of 4 theta.
Okay.
That's beautiful.
There we go.
Now, arrow to the left. I've forgotten if this works. Arrow to the left to the marking for the curve.
Yes.
Just before the color.
Yeah.
Yeah, there you go. So hit enter.
Okay.
Now, can you change
the color?
Move down 1 to the line.
On the show. Well done. Hat tip, man. Well done.
So can you change that to the little ball and line so that you could actually see the graph being traced out? That's the one.
Yeah.
That's the one. Yeah, for sure.
So I'm just thinking that, Vicky, would that help us see too how the point on the curve is getting closer or farther away from the origin?
I think so, definitely.
All right, let's take a look at it.
Okay.
I'm going to go ahead and make a graph.
Yeah, that's cool.
Yeah. So this kind of
I think
gives you the
that's very
sense of
nice.
what happens with a spirograph.
Yeah.
You don't have the ring and you don't have the disc with the, the hole that you put your pen in, but you can envision, if you've ever played with a spirograph, you can see this curve evolving through
Yeah.
that
Yeah,
technique.
that trace ball is really handy for that.
And I would,
Hey,
as teachers, I would definitely demonstrate this.
for
Yeah, I think
sure.
something that's maybe
For sure.
unexpected here is the order in which those leads
Yeah.
were completed is it wasn't just working around
Yeah, it's not
that
pedal, pedal, pedal.
Yeah. It's not just working clockwise or counterclockwise. Yeah, you're
Yeah.
right. You're
Yeah.
right.
Yeah,
You're
it's just,
absolutely right.
rolling around this, which I find it fascinating. This is one of my favorite things to teach. So,
It's a
I
little
love it. I
counterintuitive,
love it.
isn't it, Vicky?
Hey,
Huh?
yes, it is.
Tom,
Yes.
there was a question in the chat. Could you do the list for the coefficient? The answer is yes. I don't know if you want to take the time to do it, but you could demonstrate that if you wanted to put a list in there.
Why not? Okay.
Just do a simple one like 2
Yeah.
and
Do
3.
like
I mean,
do 2
yeah,
and 3 or 2 and 5 or something like that.
We'll just do a
where you
2.
can kind of see the difference between the odd and the even. And I think this is one of the things that is coolest to me, because now you have that trace ball on there.
Okay.
Let's
give
see
it a
what
shot.
happens
See what
here.
See
happens.
what happens. Yeah.
Let's see what happens.
So it's going to do these sequentially. So it's doing one curve completely first.
That's right. It's doing the 2 first.
Okay.
And then we'll start over with the 3.
It's
And
retracing it, isn't it?
I think that is so revealing about
yes.
what is going on. The
Yeah.
difference between the odds and the evens.
Yes.
And what are we doing when we go from 0 to 2 pi?
I'm almost afraid to ask her. I don't know if you know this off the top of your head. So is it possible to put a list in both places?
Sure. Let's find out.
Okay. All right.
We may create quite a design, but
We may create all kind of a disaster here, but let's
yeah.
see it. I'm curious too. I don't think I've ever tried doing that. You need the curly brace.
I need the curly brace. Yes.
Yeah.
And then let me get the insert key.
So although Curtis, Tom is actually physically putting the list right here, you could set that up in the stat list editor, right?
That's what I would do. Yeah,
Okay.
That's what I would do. I mean, Tom's putting the lists in here, but normally I think we would do it when we just do it in the stat editor.
Okay, gotcha.
All right, so we have radius 3, and the coefficient on the theta is 2. Now we have radius 4.
So it's doing both the first list that appears in the expression. It's going through those two values.
No, I thought what it was doing. So it's going. I anticipated that, but I wasn't certain. I didn't want to say anything till I saw it.
Well, I wasn't sure at all. I was an honest question on my part. Setting it up.
So I
didn't know if it could handle 2 lists at once. Yeah.
Right. But what it's going to do is it's going to iterate through those lists. The index being 0, and then, or sorry, in this case, I guess it's index is 1, and then index is 2. So you're going to get the 3, 2 and the 4, 3. But you're not going to get the 3, 3 or the 4, 2.
Got it. Okay. So it's not doing like an array of. Okay.
Right.
All right. That's good to know.
Means
I learned something new.
I think that your lists need to be the same dimensions.
Oh, okay. That makes sense.
Yes.
Okay.
So it'll match up nicely.
Right.
All right. Very cool. Okay. Well, let me.
That was a fun exploration.
Yeah, it was fun. Well, I know Steve has another problem, so let me share.
I got lots of problems. All right, I'll try one more. Here we go. Let's see. All right, I do indeed have one more problem, and this one deals with a polar function defined by r of theta equal to 2 minus the sine of 3 theta. So this one's a little different than the first two. We've got kind of a difference of two terms here. It says, suppose r is measured in inches. I feel like there's a rate coming here. So the first thing is, let's see if we can find the average rate of change of r with respect to theta in that interval. Kind of a weird interval, 7 pi over 12 to 3 pi over 4. Okay, so I picked that so that the argument of that sign would work out reasonable so that I could actually do this one by hand without going to the calculator. Well, over here is my expression for the average rate of change. R of 3 pi over 4 minus R of 7 pi over 12 over the difference in the denominator. And so, okay, I've just got to, if I'm working this out by hand, I've simply got to plug in these values for theta into the original expression. I think I did that here. I did a little bit of simplification in the argument in this step and this step. And I think I got a common denominator down there in the denominator. And let's see, I evaluated the sign in both cases. I did a little bit of simplification. I think I distributed that minus sign. I think in the denominator here, I did some subtraction. I think that gave me a 2 pi over 12, so that's a pi over 6. The 2's cancel. And I have to be careful with the minus signs here, but I think this is correct in the numerator. It's a minus square root of 2 over the pi over pi over 6. Division of fractions, I took the reciprocal of the denominator and multiplied. And that's I think, the exact symbolic answer. And Vicky helped me with this a little. But after I wrote this, I thought, this would make a nice multiple choice question, wouldn't it? Okay.
It would be a good tough one.
It'd be a nice multiple choice question. Okay. So let's see, what are the units for the rate of change? Oh, pardon me. Before I get to B, I just wanted to mention Tom may get the opportunity to do a little bit of this with the TI-84, but if you were using, for example, the TI-Nspire, and correct me, Curtis, if I'm wrong here, but I believe the Inspire will return the exact symbolic answer if we do this. So that if we actually ask the Inspire to compute this expression without any decimal points in those numbers like the 4 or the 12, jeepers, I think it will come back with that exact symbolic answer, which is just amazing, just remarkable.
Only the CAS version.
The CAS.
The CAS version, yes. I'm
CAS
sorry,
version.
the CAS version. Yeah, right. So
And
what are the
students may use the CAS version on the AP pre-calculus exam.
That's
They
right.
sure
Do want
can.
to remind you of that.
Very good. So the units here, well, this is a rate of change. If I've got this correct here, I think it is inches per radian. It's kind of hard to think about, but R is changing. R is measured in inches. This is a rate of change with respect to theta. So I believe it is inches per radian.
Yes, and I think it's important.
I'm sorry, Vic. Go
I
ahead.
don't know that this would be a question on the AP exam, but I think it's important for students to understand that that's why we have radians. I mean, because we need this kind of unit of measure. So maybe it helps them to realize why we ditch degrees when we get to AP pre-calculus.
Why we ditch them? I like that. All right, let's see. C simply says find R of 2 pi over 3. So I plugged that into my expression and I did a little bit of simplification here. Sine of 2 pi is 0. So that value is just 2. So let me just think about this for a minute. So this point, let's see if I've got this right. R is 2. Theta is 2 pi over 3. That's an ordered pair in polar coordinates. That point is on the curve. Now, part D here is a little bit trickier, and I'm going to show you a sneaky way that I thought about this one. I'm sure Vicky and Tom will have a better way to do this, but I'm going to show you a sneaky way that I thought about this. I don't exactly know what this curve looks like yet, okay? We'll get there in a second. But it says if a point is moving on this curve, as theta increases, you think the point is moving towards the origin or away from the origin, or towards the pole or away from the pole, when it's at these coordinates, R of 2 pi over 3, 2 pi, well, we know this is 2 pi over 3. How do you know what's going on? Well, I've got an answer there, but let's see, how the devil did I get that? Here's what I thought about, okay? So what I'm going to think about here is I'm going to evaluate this expression. I'm going to evaluate the sine, let's see here if I've got this right, of 2 times, let's see, do I want 2 times that? Yeah, the sine of 2 times, no, sine of 3 times 2 pi plus a little increment divided by 3. I've got to make that a 2. I'm sorry, let me do a little bit of erasing here. See if this works. I had to think carefully about that. My d is just a little bit of an increment, and I'm going to rewrite that. I think that's what I did. I took the sine of 2/3, 2 pi plus a little bit. And I thought about that. And so what's happening is that little increment d, that little delta, increases, gets a little bit bigger than 0. So 0.1, 0.2. What's happening to that argument? Well, let's see. The 2 pi plus that is getting bigger. So let's see. And then I'm multiplying by 2/3. So I've got a positive number.
Steve, shouldn't that be 3? Shouldn't
Pardon
that
me?
be 3/3? Shouldn't that be 3/3?
Oh, I think it should. I apologize.
Yeah, make it a little easier to think
It's
about
even
this.
easier to see, isn't it? Yeah. Let's make that a 3. And now it's even easier to see. Thank you, Vicky. I apologize.
Well, so it'll be 3. Yeah. Okay.
So now it's just 2 pi plus a little bit. And what happens as that d increases? Well, you can kind of see this in the first quadrant. And that sign of that argument is getting bigger. So if that's getting bigger, what's happening to this? Where'd my expression go? What's happening to my expression? R equal 2 minus the sine of 3 theta. What's happening to this whole expression? Well, the sign of that argument is getting a little bit bigger. 2 minus that, it's getting smaller and positive. So as I'm near that point, 2 pi over 3 and passing it, I can see that R is positive and decreasing. I'm getting closer to the pole. I'm getting closer to the origin. Holy Toledo, how about that? Now, there's probably a nice way to look at this on a graph. There's the graph that I produced here. I've got a couple of points on there that I think correspond to, if I've got this correct, I think correspond to a 7 pi over 12, a 2 pi over 3, and a 3 pi over 4. How about that? And this isn't really a 3-leafed rose or a 3-leaf clover or anything, but kind of a different, still there's some symmetry here in this polar graph. Very cool. Tom, you have one last bit of technology, or are we good?
Yeah, Steve, I think I can show something real.
Okay, cool.
So let me share my 84 screen again, and I think I've entered the function you were looking at. Let's just do
Looks
a
good,
reality
Tom.
check. We'll take a look at the graph. Yeah, it's matching
Very
up
cool.
what you got. And just the one thing I'd show folks, I've actually gone ahead and done the calculation on the calculator screen, but I will show you retrieving a value. We go to the calculator screen. What I've got here is I calculated that rate of change.
Yep,
and
cool.
Of course, it's returning that final calculation in decimal form.
Yep.
But just if I wanted to look at, say, R of 2 pi over 3, what is the actual value? If I go to the bars menu and go to Y bars, it's actually any of these function types. So we see function, parametric, polar is the third one. So let me enter that. There's R1. And so I've got R1, and then I could put in a specific value for theta, like 2 pi over 3. and we can see what
Hey, how about that? Got the same value.
Good. That's reassuring, to be sure.
Yes, it is for me. Yes.
So, and looking at that graph, I almost wish we were looking at yours, Steve, but those three values, they were kind of
Yes.
on the left side of this upper pedal.
Yes.
They were like going almost in a vertical line. No, not quite, but the R value was really decreasing quickly as we were moving down that. So, and as I remember, we got a pretty large rate of change going there in your part B.
So
Okay.
again, the graphing with the, I don't know, the little ball with the one that shows the pattern. I think it
Yes.
also reinforces for students that understanding of what's actually happening when we talk about this rate of change.
Yeah, I can do that real quick.
There you go.
Here. Yeah, that's a good point. Let's graph that again.
Fast, slowing down. Yeah, cool.
Really cool. And
really
I'm
do
gonna,
get a chance for the rate of speed. That's
yeah.
yeah.
And I'm also going to re-emphasize the fact that we're not doing it here, but teachers, students, yourselves can connect this to the rectangular graph and kind of see the connection. And I think that's an important visual that can help students a lot with understanding these rates of change with the polar functions.
Yes,
Very cool.
for sure.
Fine. Stop the share there. Great.
Hey, Tom, before you quit sharing,
Oh, I can get back on very
Oops.
quickly.
I got one more thing. I
All
know
right.
we're right past time, but I got one more thing. Hey, go to your editor there. Change the color of that graph to green.
Okay. Oh, I
Uh,
got all right.
we didn't plan this, folks.
No.
He's thinking ahead to Monday already.
Yes, he
Go
is.
down here. Go down here. Go to your function. Put in. Let's see. I don't know what your window was. So let's say it's like 4 or something. Sine 2 theta.
You want it changed here for the R1?
Yeah, just start typing right over the top. 4 sine 2 theta
Okay.
plus, keep going all the way
Plus
out.
outside the parentheses?
Yeah.
Okay.
Plus 4, or actually, no, don't even do 4. Just do sine of 6 theta.
Which is a great example of some of the cool curves. By
And now you can
experimenting
just
with
go
the
ahead
trig
and
function.
hit the graph key for us there. And we should see a really nice looking little picture there. And on that note, folks, we'll use that to be the sign off. I hope you guys have a great Pi
Very
Day
cool.
tomorrow. Celebrate a little bit of St. Patty's Day on Monday with some of these fun graphs that you can do. And we will see you guys here in about a month to pick up on the advanced placement pre-calculus
Get ready
exam
for the
prep.
exam. Yep.
So we'll be checking that out. As always, I'll post the solutions tomorrow. I'll
Yep.
also post the program that Tom was running to put a polar grid behind that on the graphing calculator, and I will also email you a certificate of participation if that is something you would like to have. My email address is in the chat. If you'd like to use that, you can certainly reach out to me. And enjoy your Pi Day tomorrow. I'll talk to you in a month.
Very cool.
All right, guys.
Hey, thank you. You guys are terrific. You
Oh,
are
this was
great.
We
fun.
are good.